Welcome back to separations. In the last video, I showed you how certain compositions are inattainable in a single equilibrium stage. In this video, I'm going to discuss one of the ways to combat that, which is to add more flash tanks in series. An important caveat of the statement that certain compositions are unattainable is that this is depending on the feed. So the idea here is to send the products to another stage, and because the product has a different composition than the feed, then different compositions will be attainable in all the subsequent flash tanks that you add. So this is what it would look like. For example, we have our first flash stage, stage 1. We would send our vapor product to a stage 2 with vapor and liquid products. And we could keep adding stages in general as long as we desired. Right, so we'd have some feed composition Z. We'd have a vapor phase composition Y1, which would be greater than Z. And then because this composition is greater than Z, we now have different compositions that are possible within this second stage. So Y2 would be greater than Y1. The idea is we can keep adding stages as long as we'd like. So I think the best way to look at this is with a practice problem right off the bat. So let's take this one. It says a saturated liquid feed of 100 moles per second is sent to a flash drum where half of the feed evaporates. The feed is an equal molar mixture. Not sure I've talked about what that is yet. Maybe you can understand what it means just by looking at the word. Equal molar means equal amounts of moles. So this is 50-50. With a constant relative volatility of 1.8 between the two components. So part A asked me, what are the resulting compositions of the product streams? So I went ahead and ahead of time, I've drawn for us the graph of relative volatility of 1.8. So this is the equilibrium curve. Alpha is equal to 1.8, and more specifically, the equation of this curve is y is equal to 1.8 times x over 1 plus 0.8 x. So let's go ahead and draw our process flow diagram. We'll start with the just one stage, but we will be adding more stages. So it's not obvious yet that we'll be adding more stages, but part of the problem is that we will add more. So we've got 100 moles per second of our feed and equal molar, so 50-50 mixture, therefore ZA is 0.50. And we've got half of the feed evaporating. So I don't need to write an equation for that. I can just do this in my head. I've got 50 moles per second of vapor product. And then because L plus V must add up to F, I also know that the liquid side is 50 moles per second. And therefore, I've got two unknown variables. I've got YA unknown and XA is unknown. And then really quickly, before I go on, I want to address something that I remember saying in a previous video that may be confusing. So I want to explain this a little bit more. If you look at the degrees of freedom, I said that Gibbs phase rule has to be specified, right? So by Gibbs phase rule, I've got 2 plus 2 minus 2 is equal to 2. So that's 2. That's always the number that's out front of Gibbs phase rule. 2 plus 2, the number of components, minus 2, the number of phases, is equal to 2, which means I have to specify 2 of the intensive variables in order to specify the system. And in this case, XA and YA are unknown, so therefore, in order to specify the problem, I must know what T and P are. Yet T and P are not given in the problem. So how is it that I can still go ahead and solve this problem even though I don't have T and P? So by specifying the relative volatility as 1.8, that is an implicit stating of what the temperature and pressure is. In other words, these two components only have a relative volatility of 1.8 at a certain temperature and pressure. So if I change the temperature and pressure, I would have a different value of the relative volatility. Or maybe I wouldn't, but so pressure, for instance, doesn't change the relative volatility all that much. But importantly, setting the relative volatility is equivalent to setting the temperature and pressure because it's just setting what the conditions are for equilibrium. So that's an alternative way that you can satisfy Gibbs phase rule. Okay, back to the problem now. I want to solve for YA and XA, so I'm going to do this graphically. before I do it graphically, I just really quickly also want to point out what the limits of this column are. So at z is equal to 0.5, I know that this is a point that is on my material balance line. And I know that the operating line, y is equal to minus L over V x plus F over V times z. This is going to be the equation of the line, and I know what L over V is. I know that L and V are the same number, so the slope is going to be -1. I just quickly want to point out that what are the limits? Our straight vertical line, which corresponds to a y of about 0.62, and a straight horizontal line, which corresponds to an x of about 0.34. All right, so I know that my composition has to lie within those bounds. So as it is, I know what my slope of my operating line is. It's -1, so I can draw a line of -1 from the point that I know lies on the operating line. So a slope of -1 is easy. You just connect the corners of the squares. And by seeing where the intersection of the operating line is with the equilibrium curve, that would get you your answer. So I'm going to draw lines across here such that I can read the values off of the graph. And even though I have a grid line here, I'm having difficulty following it. Okay, so I've got about 0.56 and about 0.42. So I'm going to fill those in on the graph. 0.56 and 0.42. Now, these compositions are not all that changed from the initial feed composition. So we haven't really approached pure at all. We've just kind of purified a little bit. Okay, so part A is solved. Moving on, the problem says you desire to increase purity of the more volatile components. So you decide to send the vapor product to another equilibrium stage where this time half the incoming stream is condensed. So we've got a saturated vapor here, and we're going to condense half of the feed. So in another stage, pick a different color. In stage 2, I'm going to have vapor and liquid products as well. And it says that half of the stream is condensed, therefore I can still do it in my head. I know that L2 is 25 moles per second. And also V2 must be 25 moles per second because material balances must close. And I have to figure out what my YA2 and my XA2 are. All right, so I'm going to do this again graphically. I'm going to do it on the same graph, just with a different color. So I'll keep my blue pen. And this time, my Z coordinate is 0.56. So when I'm looking for a point that is on my operating line, I can go to where on the y equals x line, I've got 0.56. So that is going to be up here, if I can follow the line correctly. Right, and you should see that it should be the same y coordinate as the answer that we got from last time. So this is my Z. This is ZA2, or alternatively, YA1. Not YA12, YA1. Right, because it's coming from the first stage and becoming the feed to the second stage. So I'm vaporizing half the feed again, therefore my composition is going to be, my slope is -1. Having a hard time making sure my line is straight. I don't think I read this graph right. Maybe it's 0.57, but getting too detailed here. It's hard to read this graph, especially with the Surface pen. Anyway, my slope is -1. And that is because, again, L is equal to V, and therefore I can read the compositions off the graph. So importantly, I've got a YA2 that is greater than YA1. Now I'm at 0.62 and 0.49, we'll call it. So these are going to be the compositions out of my second stage. 0.62 and 0.49. All right, so look and see what we've done so far. So we've gone from 0.5 of A, we are now at 0.62A. So we're getting purer and purer with each stage. So from the second stage, I've got a vapor That is 62% A, therefore 38% B, and a liquid that is 49% A, therefore 51% B. Okay. How many equilibrium stages operating in series would it require to reach 75% pure component A? So at this point, what we can do is keep adding stages to our process flow diagram and keep going like this, or this is how solving a problem graphically can really help. So where I'm going to make the key assumption that is not stated in the problem, that I'm going to keep splitting this product stream in half every time. And just simply by reading on the graph, I'll do a different color for each stage. So I'm going to come across here. This is going to be my ZA3 equals YA2. And I have a line of slope minus a half. This gets me up past 0.7, but not quite 0.75. So I'm probably going to need one more stage here. And I think this one is going to indeed do it. All right, so pretty close here. So on my fourth stage, I've got a composition of about 0.77. So 4 stages it's going to take. And I did that again by going quickly once I recognize what the pattern is by solving it graphically. All right, so what are the advantages and disadvantages of operating your process in this fashion? What would you suggest to improve it? So the advantage, I hope, is clear, that you can get to a purer purity than you could with a single stage. Remember, at the very beginning of the problem, I looked and saw what the limits of purity were for a single stage. And I think I saw that 0.62 was the maximum I could get for YA with a single stage. So by having 4 stages, I've gotten to 0.77, which is much greater than originally. However, the problem is if I keep going like this, if I do 2 more stages, I'm going to have 12.5 moles per second of product in the 3rd stage, and then 6.25 moles per second from the 4th stage. So my product amount is decreasing every time. Remember that there is a trade-off between amount and purity. So what would you suggest to improve it? Just looking at the process flow diagram from the first 2 stages, if I'm looking at this stream in particular, it's not going anywhere. So a much more efficient way to solve the problem, and furthermore, the composition is about the same as the feed. So instead of just sending this to nowhere, I'm going to recycle this and put it into the 1st stage. And that, of course, is going to throw off the material balances of everything else, right? So I'd have to erase all my balances and then work out what the new ones are. So if I now had 100 moles coming in plus 125 plus 25, I would then have 125 moles coming in, which I would then have to split into 2, and then I'd have to keep going to iterate to work out what the flow rates would be. So that's going to be all for today. Just going to introduce the idea that we're moving on to distillation columns next. And a distillation column is nothing more than a series of flash tanks in series where you are recycling the stream that you don't want to the stage before. So it's a much more efficient process than just having several flash tanks lined up in series. So that's all for this video. I'll see you in the next video.